Okay, I will talk about our lab 8, what we have done, and let's first see our basic principle of the lab 8. In lab 8, we will finish on network processing and and also this network processing will own our smart NIC uh, and here we will have a, network flow coming here and the network flow go out, and here we will deal with our network data in here. And uh, in, let's first talk about our uh, our basic idea. In here we have a simple fivefold in here. This fivefold will handle the network packet uh, coming to and stored in the BRAM, and when the BRAM is stored totally one network uh, packet, which may be the 1050 uh, bytes, and it will uh, it will pull out a signal uh, and give the CPU to and it will put out a signal, and the CPU will receive this signal and hand out and hand out those data, and maybe it will give this data to the GPU to processing, or maybe it will directly write back this data into our VRAM, and after our deal with this network packet, and we can uh, string we can transfer our data uh, go to the network outside next hop, and here is our basic idea. And mm, so we let's go explain our design from top to the down. And in the top, we initiate our user top modules uh, in here, and here is our network processing. This module is this module that, and we initiate in here, and in our user tops we will have two basic CPU and convert 5 volt, and later we will have a GPU in here, and mm, they will have a handshake protocol to communicate. Um, for example, when for example when uh, when this convert 5 volt have a this signal is active, it means CPU can deal with deal with our network packets, and we will tell CPU you can do something, and CPU after CPU finish something, it will give back the signal called CPU process down, and give back to the FIFO, and the FIFO will receive this signal and do the next action. In, maybe it's transferred and such like that. And in our convert FIFO, let's check in here. In our convert FIFO, mm, we have we just have a basic two state in here. Uh, One is the can threshold signal is 1. It means you already have a old wall. Here we deal with our data in the wall by wall, no packet by packet. Such like that. We have a whole packet in our front end. In our front end, our front end is the uh, uh, our front end is the here. Uh, we have lookups, and we have our whole packet in here, and we have data. Oh, by the way, let's talk about the data plan and the reg plan. In data plan, we have a data control. This is 4-bit, and here is 8-bit, and one WR signal is 1 bit, and one back pressure signal ready. It will tell our upstream module, maybe it's upstream, right? Upstream module don't receive any packet until I finish my job first. And here is the four important signal in here. And let's go back to our convert FIFO. Our convert FIFO in here, we will store our network data word by word. Here is one word, and one word, and we will store it. And if the convert FIFO still dealing with one word, it will uh, it will go this state. And if it didn't hold any it didn't hold any packet, it means the hold value is the 0, and it will directly absorb the data from the upstream like that. Maybe check this track state machine is more clear. We have two uh, stage. One is the hold value, and here is the hold value equal to 1. And if the can flash hold and accepting, this accepting means the job FIFO is can absorb the next word, so we can flash the inside the data and absorb the next word. I don't sure I explain clear, but I will upload this state machine to our GitHub and add some details later. And here we will in Convert FIFO we have a simple two-state machine, right? And then we will give our data to the job FIFO to deal with. In job FIFO is our is important. We have 4 states in our job FIFO: ideal state, and a few filling state, and processing state. In processing state, we will give our data to the we will give the our give the right to our CPU to deal with our data, and after the CPU finish, we will go back to we will go to the drain logic, and the drain logic will send the data out. And in here in our job FIFO coding, we use the three-state machine, final state machine way to write our FSM. And here is the uh, state transfer and state transition, and those signal will change in here. Uh, let's pick some details to talk. For example, let's talk about oh, let's talk about here. As you can see, I still remain the job P, PKT logic in here, which is we are finishing on our lab 3 or lab 4. I forget the IDS module, but in here we always keep it 0, so we didn't have a job logic so far, but in future maybe we have. And mm, so this viewing state will observe our data until it's the last row of our packet, and we will go to the processing. As long as it's not, we didn't need to discuss our packets, and we will go to the process state. In process state, we will only waiting the CPU down, and in future we will maybe we have a GPU can directly control the display run without the CPU, but now now we didn't have. And mm, mm, let me see. Um, Here is the drain logic. Uh, Here is a write printer RP, and here's a read printer, and here is a write printer, and like that. And uh, let's talk. Here we have a two FIFA event initiated here, white, because uh, we only let the CPU to modify the lower uh, to modify the CPU modified the lower 4 bit, and uh, higher bits will remain the remained. We didn't change, and mm, okay. And when our state is as processing, and our proactive signal will be 1, and in here signal will be 1, and proactive signal will be 1, and will tell this tell the CPU to uh, tell the CPU to work. And in our user top, or maybe it's a little late, but I forget to talk about our module hierarchies. We have a user top, and in our user top we have a FIFO, FIFO have a drop FIFO in here, and we have a CPU, and they will communicate by the handshake protocols and such like that. I just forget to talk about. And I think uh, the code is enough to talk so much, and the detail all the code I have uploaded in our GitHub. Uh, this native J CPU, and we also modified our CPU from 32-bit data rate to the 64-bit data rate. In here, you can see our already 64-bit data rate. And oh, by the way, I need to talk about how our CPU down signal be active in here. CPU down signal, and when the proactive is here, and our is down store signal is here. What's our is down store signals? In here, we just simply have a agreement for lab8 when our CPU is trying to store our 800 hex 800 address. It means we will give our it means the CPU is down, so so the second so we just simply create this algorithm, and later we will see that our test bench will have such action, such things, and that's totally that's all. And and I think that's all. And let's continue to talk about our behavior testing first, and later I will talk about our post behavior testing on the net FPGAs. And we can just use the Vivado to testing our code because it's just a behavior testing and RTL testing, so we don't need to open our ISEs. And I already import those source and test bench. And in our test bench logic is very simple. It's just a simple unique test. We have in data. Wait. In here, we have we first need to initiate our iCache, or say the iMemory in our CPU. Yeah, we didn't initiate our data when we didn't initiate our data for our CPU iMemory, so we need to initiate it first. And as you can see here, is actually the LLT Wait, I forget. Um, yeah, here is our LT, and uh, I store the one in here, and LUI LUI instruction in here, and which is RV15, and we have adding, and it create uh, our agreement in here, uh, and we store this address, and that means our CPU is down, and so which is the totally, which is the uh, our initiate in here, and here is the so we didn't in this test we didn't have any programming in our CPU. We just basically checked the connectivity and the state transfer is correct, and our same pack testing, and we in our first package we have FF, which is A1 in here, and we have contact is 111, and rest in the remain package in the remain words is 000, always zeros until the next packet is control is the FF, and uh, it's just a very simple testing, and in our testing began, and we send our packet to our DOT, and waiting the it absorbed all the packets, all the words, and let's check the function is correct. If all correct, it will pass. We just simple check the header. Uh, okay, we didn't talk. We talk so much too much. Let's direct go to run the simulation. Okay, and yeah, as you can see, we get our package. Uh, it's totally same with same as the our same as the our package in here. So it means our behavior testing is passing, and mm, we also I also write another test bench, mm, which I just preload adding programming in here, and for the first words we add one, and remains always adding one for all each word, and And also we have a PC down to make our PC down signal is active. Mm, and we send our pack, which is 1, 2, 3, 4. And let's check the if our will get 1, 2, 3, 2, 3, 4, 5 or not. And let's run. Mm, okay, and uh, we play some back, but I just forget to close the previous simulation, and you have some buggings. And on our test bench, I didn't modify anything, and it's still uh, the same test logic before, and we can run our simulation now. And as you can see, it still have a sound, and it's still pass, and the output is get 1, 2, 1, 3, 2, 2, 2, 2, 3, 4, 5, and mm, on our TV, um, we have a 1, 2, 3, 4 initiate, and that's our behaving testing, and mm, after behaving testing, uh, we have our post behaving testing. Mm, see, uh, I create a general rank for us to check those signals uh, for software signal, for software register, and for 8 high power register. Uh, and in Harvard, we can check our CPU, PC, and uh, yeah, VRAM and VRAM control. The total 72B data in here, and we on our software we can uh, write different programs, different programming programs, and uh, mm, and change our VRAM printer, change our VRAM printer, and uh, here is our VRAMs. We didn't do any initiation. Um, okay, and let's it found, and need FPGA project, and code. Um, before uh, our lab8 CPU in here. Before our lab8, we also have the pass-through version here. It means we didn't have any CPU, GPU in here. and we only have the our GPU. We only have our 5 volts, and to test its connectivity. And I also upload in the GitHub. Mm, let me see. And go to the lab8 CPU, and here source. Here is the all the project source that we have. Um, and include we have a project XML and the top user top XML, and we can check our user top XML. We just declare the order software register and hardware register in here, and the project XML will uh, project XML will uh, instance in instantiate our user top, and because we already uh, run the it fell before. mm, uh, let's check the log, the make file log, and we don't have arrows, and go to the down. We don't have arrows, and the bit file also generates successful. And I think the here also have the um, timing reports going here. Uh, you can go to the P TR, and all the timing report show us the all the constraint on meets. Um, and our here is our uh, yeah, I think here is our uh, design, and it's a 9.7.9. The critical path is 7.9, and we don't have any slug. And mm, that's it files, and let's go to the net FPGA. I already upload our uh, lab8. Here is a pass-through bit, which means we didn't have a CPU, and the 0 and 1 it has a timing violation, so we didn't use it. And two, the version 2 is without any timing violation, and it can run successfully. But first, let's why so lag? Let's first run the pass-through version first. lab8 faithful pass through and RKD because it's pass through and we just in here we just connect our data into our FIFO and go back to from our FIFO and that's it. So we checked our state machine, this first state machine work correctly and I already opened the RKD and let's ping the 10 to 4 3 and it shows we can ping our pin the node 0 from node 2 is successful and that's a pass-through verification and mm, RKD and let's download another bit file CPU to bit file. Mm, hmm? uh, it's string scripts lab8 and in lab8 we have two scripts. One is to load our program to into the cache, and another is the script. You can check. We have a address in here. Uh, okay, it's running now, so we can uh, yeah, we have a address. I already copied before. Mm, mm, user top, we have a 9 register registers in here, and so I can have those common to um, those common to uh, to how to say to access our our design signals. So for example, user set and let's check the status. We have FIFO vote alright or not. Those are debugging signals and the PC down and VRAM valid and the FIFO state that's important and packet length. And we also have the correct to check the our 9 rack. And this two module is uh to is to is is to change our work models. Uh, 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 in here we just bypassing is like here Uh, for example, we go go here and just bypassing if the, for example, if the packet is SSH, which is a very safe 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 protocol, so we can totally trust it and didn't need to CPU to deal with. And via module is CPU, it means we must go uh, we must give back uh, our data to the CPU to deal with, and mm, it's a right iCache logic. Okay, and also same with the pass-through. We first test the its connectivity, and uh, maybe let's change to the module pass-through first. And I forget something. Mm-hmm. Already it's bypass. Wait a moment. Okay, I'm back. I'm not sure what happened just now because I tried to paint by myself, and it actually is work. Maybe it's the network problem. So um, let's try to re-download it again. And now mm, we have we download our bit file first, and then we use our script to reset and change the model to the bypass, and check the state chips is ideal, right? And we can print. Oh, RKD opened and print 24, and now it's working. So it's actually working. So mm, and and now let's try to Um, Now we are is the bypass model, right? So we need to uh, now we only test the bypassing test, and we need to test in our CPU. So I have this script to load our um, load our iCache, load our iMemory and the dmemory hex file. In this hex file, uh, it's show like this way. In this hex file, actually, um, it's the device file, and which is simple programming testing. It's a LUI, and add and here is store words and like that. So uh, we first load it, use the you have better to use the this to keep it bypass first. Uh, and now it's loading. Mm, we also have down comment and the 512 word is loading and let's uh, let's reset it and change to the model CPU. And check the status and PC down now is 0 right and we use a new RTD and the new RTD and here we also pinned our node 0 also is pinnable and now let's check the our status again. We can see amazing thing is happened. Our CPU down is 1, so it means the data is actually go stored in the VRAM and go to the CPU. And we also can use a simple iperf instruction to check. Uh, Here, yeah, and we get our message. It's a transfer function is work correctly, and now we have better to try another programming to let it work incorrectly, which can prove our CPU is actually can modify our VRAM data, right? So here are KD, and we load a new data first. iMemory cache, and the new data is the here, which is the same with our test bench. Before we test each We add for each word in stored in our VRAMs, we add one to our we add one. So if we send a 1, 2, 3, 4, we get a 2, 3, 4, 5. So just simple. Load text file. Um, uh, and we set it. Status. Switch it on is 1. Now is 0. Original is 1. And uh, we need to change to the CPU model CPU and open the GT and also create a service and use the client to send a packet and now it's amazing warning didn't receive the acknowledgement from our service. It means the data have been modified, so we cannot receive the data from here.